Welcome everyone. Today, Pawel Idziak from Jagiellonian University of Krakow will tell us about circuits over finite algebras. Please.
Thank you. I think I need to switch off the other device because we have some troubles. But anyway, thank you to the organizers for organizing these cycles of seminars. That's already the third year, isn't it?
As old as the pandemic.
Yeah, and thank you for inviting me to give this talk. And as you can see, some of the results, or actually most of them, were obtained in with people listed over here. So Piotr Kawałek, who is still my PhD student, Jacek Krzaczkowski, who spent a couple of years with me as a postdoc, and Armin Weiss, which we met at some Leaks iCalc conference in 2020, and realized that we have proved almost the same thing independently. But going to the subject, so the story actually starts with the problem of solving equation, which is a pretty old one, as you can see. And actually, I got interested in this project after a conference somewhere in Tatras, listening to a talk of Csaba Szabó, but we will come back to that. So to make things clearer, by PALS, I mean a problem of deciding if a single equations of polynomials over finite algebras has a solution. And actually, what I'm interested in is the computational complexity of this problem. It's obviously over finite babies is decidable. You need to check exponentially many evaluation to do it in not terribly clever way, but sometimes you can do it much faster. And the project is to characterize those finite algebras for which this problem is solved in polynomial time. Again, we are considering polynomials instead of term simply because, like in groups, if you have terms, you have a trivial solution by the unit element. So it's not interesting then. So having polynomials, you look at it like terms with some variables already pre-evaluated. And as you can expect, this have some connections with constraint satisfaction problem, which the problem has been already fully solved independently by Andrei Buatov and Dmitry Zhuk. And one can ask, why bother with equations? Since dichotomy for CSP is confirmed, and even we know the borderline, so simply translate it to equations. So you need some terms which commute with operations of the algebra, and that seems it's like that. And essentially, this is true for systems of equations, because in systems of equations, you have the external conjunction, which you can translate. But for a single equation, as you will see during this talk, the situation is much more interesting and exciting, I will say. So again, for system of equation, so with each relational structure, you can associate an algebra, so that CSP over this relational structures is polynomially equivalent to solving system of equations over the associated algebra. And conversely, you can go from algebra to a relational structure with the same property. But for single equation, this can be done only one way. So you can code structure in an algebra because you can build a conjunction. So internal conjunction is an operation, one of those basic operations of the algebra, but not conversely. And as you will see, unless certain complexity hypothesis fails, we don't have the converse here. Starting examples, this one was done, you can see the authors and the dates for groups where it hasn't been completely solved and still is not completely solved till now, but we made some progress. So if a group is non-solvable, then the problem is NP-complete, and if the group is nilpotent, that it can be done in polynomial times. The same holds for rings, and for lattices, the splitting line is distributivity of a lattice. The point is that this problem is language sensitive. So it really depends what you decide to consider as the basic operation of the algebra. As we have seen, this problem is NP-complete for non-solvable groups. But after listening to this, or actually during this talk, I have been actually, after several beers already, listening to this talk of Csaba, I realized that I can prove. So he was talking that for the 6-element group S3, the problem is solvable in polynomial time. And during the very same lecture, I proved no, it's NP-complete. And in a sense, both of us were correct. And we haven't proved that P is equal to NP. That's simply because what I have proved is that some additional polynomials are needed. A few years later, Csaba with his student, Gabor Horvat, shown this for the alternating group when they added just the binary commutator, which is nice, but anyway, the problem is that you need additional operation, and here is the explanation why. If you look at the size of the input and you write it, so this term here above, if you write it using only the multiplication of the group, then that its size is exponential. So it's pretty much inflated. While if you write it not as a syntactical tree, but as a circuit, which you can see here, the size is linear in the number of variables. And this inflation of the size of the input made it possible to prove that there is a polynomial time algorithm, but polynomial with respect to this inflated input. We don't like problems that are language sensitive. So what we did, we defined a couple of problems for circuit razors and polynomials, and that's essentially it's the very same problem, but the size of input is measured in a different way. So in a sense, it reduces to the setting in which you can add finitely many polynomials and treat them as basic operations. Here are the problems. So we have circuit satisfiability. So in a sense, you get two circuits and ask if you can evaluate the input gates so that the outputs are the same. You may have a system of such circuit, and here's an interesting thing, because the answer is slightly different, and it's in between the first one and the second one. So you get a couple of circuits or one circuit with many gates, and you ask if on all of them output gates you will get the very same output. The dual problem is equivalence of polynomials, or you ask simply if two circuits compute the same function. You'll see more of those problems in a while. So when we go back to groups, then there is for polynomials there is this gap between solvable and nilpotent. So if the group is non-solvable, it's hard. If it is nilpotent, it's tracked up. But if you go to circuits, then there is no gap any longer. So nilpotency is the splitting line. As I said, the problem of characterizing groups with polynomials, so you cannot somehow shrink the inputs, is still open when asked for in original language, that is with multiplication only. After several years of struggling with this problem, we came with kind of a result for algebras from congruous modular varieties. And we noticed that there are essentially two reasons for tractability of this problem. One of them is super nilpotency, which is in groups the same as nilpotency. The other one is distributive lattice-like behavior. You will see it in a while, or maybe I will say what I mean by that. We essentially forced the algebra entirely of type 4 to be a subdirect product of two-element algebras, each of which is polynomially equivalent to a distributive lattice. Sounds complicated, but in fact it isn't. And obviously, if you have algebras with tractable problem, then the product for them is also tractable. But essentially, what we have done here is summarized in this table. Equivalence of circuit is tractable if it is super nilpotent. That was already observed by Erhard, Eichinger, and Mudryński. And if it is non-nilpotent, we have proved that it's intractable. But still, there is a gap in between. It was a gap. Because very recently, we fill this particular gap for equivalence of circuit, and you will see the answer. It's neither super nilpotency or nilpotency is the splitting line. It's something in between. For circuit satisfiability, we have tractability exactly in the case if the algebra decomposes into a super nilpotent one and this distributive lattice-like algebra. Here is the same gap, right? We have it is intractable if it is non-nilpotent times DL-like. So again, there is a gap between super nilpotent and nilpotent. If you have system of equations that was already known for a pretty long time, essentially, for affine babies is tractable and otherwise is not. But if you have a couple of output gates and you want all of them to return the same thing, this super nilpotency or nilpotency reduces to be affine. So again, we have this decomposition into a direct product. And that was essentially known in 2018. I said essentially because then we improved it and yeah. But still we have this gap nilpotent versus super nilpotent babies. Okay. The hardness part of those results, as shown obviously with commutator theory and time congruence theory, there is actually more than a dozen constructions eliminating a bad local behavior. Obviously, if you can find type 3 somewhere, then you can encode Boolean satisfiability there, and it's hard. Then we separated types 2 and 4 with transfer principles. So that gives essentially the decomposition. And then we focused on solvable babies and type 4 babies, and shown that solvable has actually to be nilpotent, and those type 4, if subdirectly irreducible, they must have only 2 elements, and that was it, essentially. But there is more than a dozen constructions proving that. And polynomial time algorithms are, in these cases, are essentially done by narrowing the search space. So what you can see here is that the existence of a solution is equivalent to the existence of a solution in a small set. By small, I mean of a polynomial size, polynomial in terms of the number of variables. In distributive lattices, it's simply like if you have a satisfying assignment, then sum of constants assignments is satisfying. So you have to check only constantly many essentially solutions. So the search space is pretty small. In super nilpotent case, the first of our proofs essentially modeled somehow on Russell's proof, Goldman and Russell, was using Ramsey type argument. So this degree of the polynomial obtained here was obtained by a Ramsey argument, which is pretty huge. But then a fascinating race for decreasing this degree started, and we end up with a linear size of the search space, but for a randomized algorithm. So now I want to focus on but by looking into this gap. So what we do know now that super nilpotency is not necessary for tractability. On the other hand, nilpotency is not sufficient for tractability. And the example is in here, namely, if you take the group Z3 with additional unary operation modulo 2, then satisfiability of circuits is in P, but this cannot be solved in polynomial time using this narrowing the search space to a small one. The proof is completely different. A couple of years later, in 2020, we have constructed examples of algebras, nilpotent algebras, in which circuit satisfiability is non-tractable unless exponential time hypothesis fails, and this exponential time hypothesis is stronger than P not equal NP hypothesis. It simply says that satisfiability requires not super polynomial time, but essentially exponential one. And again, the point is that this conjunction is or is not expressible. For example, if you look into groups and you take, let me see, this operation here, like commutator, then the action of the variables here, x2, x3, and xn on x1, they do act like a conjunction. So it's not really conjunction, but if you fix A1 to be some of properly chosen constant, then the action of the rest of x's is somehow reflects the conjunction, and that's important thing. But in many algebras, like in nilpotent groups, you don't have such conjunction. Essentially, in super nilpotent algebras, this conjunction is reflected by so-called commutator terms. And in super nilpotent realm, the arity of those commutator terms is bounded. So you can express only a conjunction of bounded number of variables. But in some nilpotent, but not super nilpotent algebras like this group Z6 with modulo 2 unary operation, you can express arbitrary conjunction. The point is that this conjunction has exponential size. And here's another observation, pretty connected with the previous one. So we define the super nilpotent rank of an algebra A, so nilpotent or even solvable. So we split the congruence lattice of the algebra into super nilpotent intervals. So if you can find a chain so that the bigger congruence is super nilpotent over the smaller one, then the smallest such chain, the length of smallest such chain gives you the super nilpotent rank, and that's essentially reflected in the characteristics of midi-reducible congruences. So you have a midi-reducible congruence, you have its unique cover. We are in a solvable setting, so this cover is of type 2. The traces are vector spaces over finite fields. Those fields have some characteristics, and this is the characteristics of a midi-irreducible congruence for us. And alternating those primes, like in Z6, for example, allows you to construct the conjunctions in internal conjunction by polynomials of exponential size. But again, once you alternate 3 of them, then you can shorten this exponential size to sub-exponential if you have the chain of let's say several alternating primes. I mean, here in this chain, P3 can be equal to P1, so we don't assume that all of them are different, but they need to alternate. Then what you get in here is the root of n of a bigger degree. Already for 3, this yields you a sub-exponential size of the conjunctions. More alternation, shorter conjunction, and so on. And in this Leaks 2020 paper, we provide such examples and the idea how to prove it. Michał Kompatscher claims he shown it in full generality, and actually there is a paper on arXiv with a sketch of such proof, which contains a very cute idea, and he's not using time congruence theory in it. Okay, so the title of this talk is about circuits. So I promised to talk about circuits, and the connection with circuit comes from Theorem 7.1 in the Fries-Mackenzie commutator book. What Theorem 7.1 says? It says that if you have a nilpotent algebra, let's say two nilpotent, right? So abelian over abelian, then in a sense you have an action of one module over another one. And that somehow stratifies nilpotent babies in if the degree of nilpotency is higher, then you get more levels acting one over the other, and essentially all of them are type 2. So you have those vector spaces going there. So it can be coded by something which was in circuits, in Boolean circuits, considered as those modular gates. So mod sub p is a gate which takes as many inputs as you want. So the people working in that area are saying is with unbounded fan-in, and it returns 0 or 1. So it takes Boolean input 0 or 1, sums them up, and checks if the sum is divisible by p. If it is, that you return 1. Otherwise, you return 0. And with such gates, you can do quite a bit, let's say, but sometimes you need circuits of quite big size. So another hypothesis is exponential size hypothesis, which simply says that if you have h levels here, and on one level you have 1 prime, and they do alternate that to compute n-array conjunctions, you need sub-exponentially many gates in the circuit. So it's a lower bound for such circuit computing conjunction on h alternating levels, but only modular gates. It's still a hypothesis, but we will see more such hypotheses. Well, with exponential time hypothesis on one side, and this hypothesis on the other side, with random algorithm, we essentially got lower and upper bound, which do match for probabilistic algorithms for circuit satisfiability and circuit equivalence, which in a sense shows you that they are of intermediate complexity, which is not really a big deal, because assuming ETH, you assume that P is not equal in P, right? So, and then you know there are intermediate problems, except that here you get an example of intermediate problems which is not obtained by diagonalization, but in an explicit way. Okay, so in particular, if you do believe that those complexity hypotheses hold, that you don't have the dichotomy for circuit satisfiability. So that's different from a CSP. Well, that for that reason, you don't have the equivalence between circuit satisfiability and CSP. That tells you that circuit satisfiability has a strictly bigger expression power than CSP, or system of equations or circuits, right? So the one equation has a bigger expression power because you can express intermediate problems. than the system of equations. Okay, so since you know that if the super-nilpotent rank is at least 3, the problem is not tractable, then a natural conjecture would be that super-nilpotency rank 2 is the condition we are looking for, but unfortunately not. And again, very recently, which I already said, we proved that for a finite algebra from congruous modular varieties, circuit equivalence is in randomized polynomial time if the algebra is nilpotent and the super nilpotent rank is 2. But we don't have that for circuit satisfiability, and we do know it fails. But for equivalence, we do have that. Okay. Here's a funny story. Barrington, Beigel, and Rudig constructed those modular circuit of depth 3, of height 3, and a size which is here described, which computes conjunction. Where here omega is the number of prime divisors of M. But they needed 3 levels, and we are able to squeeze those 3 levels to 2, keeping the very same size. It's a funny story because it's even better if so we consider another parameter here, the number of prime divisors of the integer m, which are bigger than the first indicator omega of m. So then we can reduce the size slightly. The consequences of what is in here, you probably don't want to go into the details of the proof, at least not now, is that if you consider such modular circuit of depth h, that the circuit as purely Boolean circuit is satisfiable if there is only one level, or the m is a power of prime. In a sense, for algebra is so it's either shallow or narrow, as we say, and the second thing corresponds somehow to super nilpotency, as you can expect, and it really does. Okay. I said that small super nilpotent rank is not sufficient, and here's an example. The example is again the group, this time Z13, with addition and modulo 2 operation. The point is, if you look at meet irreducible congruences of this baby, you have a characteristic 2 on the top, and below are 2. So it's inverse V, and below there are 2 meet irreducible congruences, one of characteristic 3, the other one of characteristic 5. That's how it came. This 13. That's that's probably the smallest such example. Okay, so coming back for groups, what we do know. We have seen that in order to be tractable for CSAT, so the splitting line is nilpotency, but for POLSAT there is this solvable versus nilpotent gap, and there are examples of solvable not nilpotent groups with polynomial satisfiability being in P, as you have already seen, S3, R4, but all known exams again have super nilpotent or fitting rank 2. And that's what essentially Armin was shown on iCalp 2020. That it has to be like that for groups by producing conjunction on 3 or 4 levels. Then we started to work together, and we did some progress. We finished this project, and actually showing that if this polynomial satisfiability is tractable, then nilpotent or fitting rank of a group has to be small, or ETH fails. We did it for dihedral groups, and here you see the characterization. Again, omega 0 is the number of, or omega O, like odd, is the number of odd primes that divide M. If you have at least 2 of them, then this POLSAT is not tractable. Those 2 items are pretty similar. The difference is that you excluded from RP or P, assuming that ETH holds, or it's randomized version. The last statement here shows that in a sense is a generalization of this Z13 case, right? So for groups, it can be expressed like that G has 2 normal subgroups of co-prime sizes, such that the centralizers of those subgroups do not cover the entire group. Then polynomial satisfiability is not in RP, obviously under some additional complexity assumption. Now, you see, sometimes it's really hard to understand what's going on here. And essentially, you have seen that Goldman and Russell show something for groups, so that not solvable groups are hard and nilpotent are easy. I mean, actually observing that not solvable groups are hard, it's really easy in this case, because in groups you need to have type 3 there, and therefore a Boolean situation, and you do what you can expect you should do. But showing that nilpotent babies are tractable, actually they show more than that. They show that program satisfiability over nilpotent groups is tractable, and this one is about program satisfiability. I'm not going to define it very precisely, but to make it easier to understand for you, let's say like that. First of all, we consider something like satisfiability from lists. So you have a list of admissible evaluation of variables which may differ between variables, right? So the variable x1 can take this or that or another value, x2 has to be chosen from another set, and so on. Then you may be interested in restricting those lists to two-element one. I put in the name of the problem is list, but essentially is a set, because there's another variation of it, which we call program set. We have two-element lists, so it really does matter the order of on those two-element sets. You will see the formal definition after a while. And then Goldman and Russell defined something like non-uniform deterministic finite automata over monoids to recognize languages over binary alphabet. And in a sense, this program satisfiability over a monoid M asks if the corresponding automata recognize a non-empty language, while the program equivalence ask if two automata recognize the very same language. So from a computer science point of view, those problems were considered under completely different names. And so the last sentence or a couple of sentences says that essentially Goldman and Russell did it for those non-uniform automata. Why there are non-uniform, or what the hell all those means? You will say here. So we have an n-array program. It's something like a polynomial. N is not the arity of the polynomial. You will see it in a while. What is the difference? So P is a k-array polynomial or circuit over A. It doesn't matter what you want to consider here. The only difference is in the measuring the size of the input. The size of the polynomial is the length of the syntactical baby. The size of the circuit is the number of gates in the circuit. Except this polynomial, you have instruction for variables, how to evaluate it. But those instructions don't simply say that the variable x has to be either this one or that one, but depend. So with each such variables, you associate a Boolean baby, a Boolean variable. We do not require that different algebraic variables are associated with different Boolean variables. So different algebraic variables may have the very same Boolean variables, and then the value of the Boolean variable decides which of those things has to be evaluated. So those functions near here probably tells you more if you have enough patience. So the inner function of such program, so you start with n Boolean values, and you end up, so it should be A here, not Y. You end up in the algebra A, and you evaluate this polynomial depending which value is taken by the Boolean variable associated, well, with the first variable and so on. So then either is A0 or A1. It looks very complicated, but if you spend a while with it, you see that actually is not. And it has an additional power that you can use. You can use a single algebra to consider languages over two-element alphabet independently of the size of the algebra A. Right? You reduce this to those functions. If you are lost at this moment, just forget. Simply look at it like restricting the possible values for variables to two-element list with some connection between these assignments. And this connection is given that the different algebraic variables may be somehow governed by the same Boolean variable. So that's essentially the connection. And I am pretty close to the end. Now we have another hypothesis called constant degree hypothesis, which is really funny. The hypothesis comes to 90s. There was hypothesis of Barrington, Straubing, and Terrier that in such circuit that you have and sub d, which means d-ary conjunction, and then two other levels, modulo m and modulo p, such three-level circuits to compute n-ary conjunctions require exponential size. If you but the arity of this end d is bounded. If you, and that's a hypothesis. 10 years later, it was confirmed if there is no this top level or initial level. So without those bounded conjunction, we do know that mod M, mod P circuits require exponential size. And again, in this paper from 1990s, Barrington, Straubing, and Terrien under CDH showed that program SAT for such a semi-direct product of a P of a nilpotent group acting on a P group is in P. So that's that somehow extended those purely nilpotent situation, which was known from Goldman and Russell, but under complexity assumption. And recently, we have shown that under both ETH and CDH, so that was done with Armin, for a finite solvable groups with the smallest conilpotent normal subgroup N, a program SAT is in RP if this conilpotent subgroup is a P group. Maybe if you want to look at it in universal algebraic terms, we go to program CSAT. Again, under both of those complexity hypotheses, we were able to characterize algebras from congruent modular varieties such that program CSAT can be solved in randomized polynomial time, and the conditions are that A is nilpotent. It's essentially two super nilpotent in a sense that there is a super nilpotent congruence modulo which the algebra is super nilpotent, and that below this super nilpotent congruence there is only one characteristic, right? That corresponds for groups from the previous slide, that this group which is downstairs is a P group. And that's a pretty strong thing because that's satisfiability, but from both of them, so the one for groups from the previous slides and this one, we got those results for equivalence of circuits or polynomials in group, namely that super nilpotent rank for circuit equivalence and nilpotent rank for polynomials equivalence over groups being bounded by 2 is the condition here. So in a sense, we close the problems of circuit of polynomial equivalence. We close the program circuit satisfiability, maybe, but well, in this slide, you see that or maybe in the previous one, you see that program satisfiability and list satisfiability are the same. That the answer are the same. Is not true in general. And since I see a couple or maybe several couples of people in the audience working in lattices, so here how it looks for lattices. So as we have seen, CSAT is in PE, even only if the lattice is distributive. The same goes for POLSAT, because here you don't have any way to artificially shorten or artificially inflate the size of the input. But list POLSAT is just a polynomial time for one or two element lattice, and program POLSAT only for trivial one. And the point is essentially that program POLSAT has additional power of expressing negation of variables, not negation as a unary operation, but you can negate variables simply by switching those values which are somehow under the influence of the Boolean things. So that's the reason. So this result is not really deep, but it looks fun. And here is what is open. For CSAT, still we have to decide which super nilpotent babies of rank 2 have polynomially or randomized polynomially solvable CSAT, and for groups that's for nilpotent thing. And that's it.
Thank you.